when we're thinking about mixtures like we've been talking about, we can think about how do quantities that we care about in that mixture, things like entropy or volume or the Gibbs energy, how do those change with respect to the concentration, right? As you change the fraction of substance 1 versus substance 2, how do these values change? And in general, we can write partial molar quantities are just of some variable y. This is not any particular variable that we care about. We write a partial molar quantity with a bar over the top of it. That's y bar, right? So that just means it's a molar value. But then we indicate that it's for substance J. So this would be 1 or 2 for our example where we have hexane and benzene. And this is defined as the partial derivative of that quantity y with respect to the number of moles of component J, holding everything else constant, holding temperature constant, pressure constant, and then any other things present, right? So this is a generic one, so you could have, this would be considering more than just, say one other component. You could have up to, infinite number of other components. But all those other numbers of moles are held constant. And so so this gives us an interpretation for understanding, right, that we write that the chemical potential for substance J is equal to dG dNJ, holding T, P, and Ni not equal to J constant. And this is what we just saw in the last video. And what this tells us, we can say that this is equal to the partial molar Gibbs energy. So this is kind of like a Gibbs energy for substance J, but it's not a constant. It depends on what the concentration of substance J is in our solution. We can write this for other things like a partial molar entropy, right? So S bar of component J would be the same thing, ds dnj, holding everything else constant, right? Holding temperature, pressure, and all the other moles constant. Or we can also do this with a partial molar volume. And what these tell us, these are almost like molar values, right? They tell you like how much, what's the amount of volume that a mole of a substance takes up. But these values depend on the concentration of the components, and so they're not constant values like we are used to for given temperature and pressure. If you look up the molar Gibbs energy of a substance, or the molar volume of a substance, if it's a pure substance, it's just a single value, right? It's just, you look it up, that's what it is at a given temperature and pressure. This is not true for these partial molar quantities. And let's go ahead and illustrate how this works. So we'll look at a few specific examples of how we could write the total Gibbs energy for a mixture, right? So if we take our total Gibbs energy, if we fix the temperature and pressure, right? We wrote out earlier that dG equals SDT. Make sure I get my signs right. Yeah, negative SDT plus VDP plus the mu1 dN1, not I, plus mu2 dN2, right? So this is the equation we wrote out earlier. If we consider a situation with constant temperature and pressure, these first two terms go to 0, and we're left with these second two terms, mu1 dN1, mu2 dN2, right? So these are right, the chemical potential of 1 and the chemical potential of 2, which are these partial molar quantities. It's the partial molar Gibbs energy. So we can say that at constant temperature and pressure, dG is going to depend on how our system changes relative to the number of moles, right? If we change the number of moles of N1 or N2, that would tell us. Now we can integrate from 0 to 1 using a scale parameter to say that dG is equal to mu1 N1 plus mu2 N2. So we use a scale parameter because the fraction of N1 and N2 can vary between 0 and 1. So we integrate over that whole range. And that tells us that G is equal to sorry, this isn't dG, this is just G we've integrated. But the Gibbs energy is equal to chemical potential times the number of moles of 1 times chemical potential 2 times number of moles of 2. We can write similar values for, say, the total volume of our system is equal to the partial molar volume of substance 1 times N1 plus the partial molar volume of substance 2 times N2, or same thing with entropy is equal to the partial molar entropy times N1 plus partial molar entropy of 2 times N2. Now, this shouldn't seem too strange. If we take molar values, right, if we didn't have these partial molar quantities, but just molar values, we would just multiply by the number of moles, and that would tell us what the value was, not the molar value, just like, what's your total volume of your system? Take the number of moles times the molar volume, you get the right. So for a single component, you have a very similar equation. But the key thing here is that, and why we have to use equations like this is that if we have a partial molar volume for a substance J, it is not the same as the molar volume, and we'll start using this notation for the star here means for the pure substance. They will often be close to each other, but they will not be exactly the same. So in the next video, we'll look at that. We'll look at how molar volumes specifically, but this applies to all these other ones, how these will change as a function of concentration in our system.